Imagine that you're a small angle scatterer and you have measured a polydispersed sample and you've collected and corrected the data, and it looks a little bit something like this. This scattering pattern, plotted here on a double logarithmic plot, shows some features, so you know there's some information there, and you want to find out more about your sample. So what usually people do at this stage is that they try to describe the scattering pattern using the classical toolbox. I happen to have one of these classical toolboxes here. You can also find them in electronic format. Now this toolbox, it contains a number of functions. It contains very many functions actually. They can be categorized roughly into three categories. Namely the shape functions, the so-called form factors. So we have here a form factor for a sphere, or we can have them for cubes, or we can have them for cylinders, and so on and so forth. Then we also have functions which describe size distributions, such as, for example, the log normal size distribution or the Gaussian size distribution. And lastly, we have the so-called structure factors, which describe the scattering between individual scatterers in your sample, and which are especially necessary in the case of dense samples. So these are, for example, the hard sphere structure factor, which is a very popular one. We also have things like linear chain. We have fractal structure factors, which you see appearing more often than not. And we have things like worm-like chains. Now these structure factors, they're very poorly described for polydispersed systems, yet people apply them nonetheless. Now what you should do is you should look at your sample and you should try to describe what your sample consists of based or using these model functions. So if you know that you have a sample which consists of sort of cube-like structures and they might be polydispersed, maybe consider combining the cube structure factor with a log normal size distribution. There we go. And if you have a very dense structure, if you have a very dense structure like this, you might want to consider adding either a hard sphere structure factor to this, or, for example, a fractal structure factor. Now, this will describe your data somewhat, but of course it will not do it perfectly, and to try and describe your data perfectly is what is most frustrating about the classical toolbox. So sometimes people get frustrated because they don't quite know what to or how to construct their classical model, and they look at their entire toolbox and they look at their scattering pattern and they just try to apply the entire toolbox to the scattering pattern. I need to clean that up now. These people might end up with a model that eventually does fit their data. For example, they have they've made a model starting in sort of the right way, with starting with sphere-like particles and combining it with a Weibel distribution and a hard sphere structure factor. But since that didn't quite fit the data entirely, they also added the pyramidal form factor combined with a Gaussian size distribution and a fractal structure factor, because that seems to be all the rage these days. Now, of course, a function like this might fit your data, but the physical relevance of this model might not be but this model might not be so applicable to the actual system that you have, because there are an infinite number of models that will fit your data, and you've just found one of them. So, as said before, what you should do is you should look at additional information that you have on your system, for example from UV spectroscopy, or from NMR, or from electron microscopy if you have it. And based on that information you should construct a classical model that describes your system that describes your real space physical system, rather than trying to fit all of the data exactly with any model you can. Now, the reason why people get frustrated, and the reason why this doesn't quite fit your data completely, even though you know that your particles consist of spherical particles and that they're slightly dense and that they should follow a Weibull distribution, is because these things are not very flexible. These building blocks, as you can see, they're quite rigid, which is not their fault, they're just toy bricks. However, on a more serious note, these size distributions in particular, they're not very flexible. They're only described using 2 or 3 parameters. So you might very quickly run into cases where such a simple size distribution no longer describes the actual size distribution you have in your data. In such cases, there are alternatives to the classical toolbox, to which we will get hopefully in a future video. So thank you all for watching. I hope the classical toolbox is now a bit more clear. Good luck trying to apply it. If you have any questions, you know where to find me.